continue our discussion of conservation laws at applying conservation laws and Newton's laws of motion to solve various problems. So, in the last couple of lectures, the focus was mainly on conservation of energy. In today's lecture, we are going to talk about momentum balance, that is the conservation of momentum. So, this we have remember in the week where we talk about the Newton's laws of motion, the review of the Newton's laws of motion. There we derived we wrote down the Newton's law of motion in 3 levels of increasing generality, and in that context the most general way of writing the Newton's laws of motion is the following. So, suppose that we have our system. So, recall that first we talk about when we analyze the mechanics problem, first step is to identify or define a system. So, this is our system, and then the so this is our system, and the rest, and this is the surrounding, and the system is interacting with our surrounding. So, this is our basic box model picture of any mechanics problem. Now, the interaction, because of the interaction, if there is some external force acting on the system, let us say there is some external force F external which is acting on the system for a time interval delta t, then the net effect of that external force is to change the momentum of the system by an amount delta p. So, this is the most general version of the Newton's law. So, here, so this F times delta t represents impulse. So, this kind of force can be a continuous force, it can be constant force, it can also be something like a very instantaneous large impulse force. So, all of these things are covered within this simple expression. So, then there is an immediate corollary that when the momentum of the system is not changing, so delta p is 0 if the total external force. So, remember that this is the total force. So, if there are more than one force acting on your system, then you have to take the total, find out the total force, or rather the total impulse on the system. So, this quantity, this F times delta t, is called the impulse due to the force F external. So, if there are multiple force, then calculate the total impulse, and so this, if delta p is 0, that means the total internal force is 0, or in the reverse way, if the total force is 0, then there is no change in the momentum of our system, which means the total momentum of the system is constant. So, this is our principle of momentum balance. Or the conservation of momentum. So, I am not I deliberately wrote in the equation in this format, because in the examples that we are going to take, we will see that there are a lot of different situations where the momentum is not simply mb, or force is not simply mass times acceleration. So, it is always important to start with the most general version of Newton's laws of motion to think about the momentum principle. Another point that I want to mention about your choice of system. So, in your box model, when there is a subtle difference. So, this is a general point about energy and momentum balance. So, there is certain subtle difference. When we talk about the free body diagram, of a system, let us say you have a two. So here is a example of two particles which are interacting with each other by gravitational interaction. So, these two particles can simply be some object like this object, and one particle is this object, and the other particle could be the earth, and they are interacting with certain gravitational interaction, and we have learned before that this is a conservative force. So, you can derive the force of interaction from a potential energy, which is shown here, where r is the distance between the particles. So, if this is our object, so r will represent the distance between the center of the earth and the center of mass of this object. Now, normally when we talk about examples where say objects are moving on the surface of earth, then we are basically talking about the like at one fixed r, because we can approximate any distance on the surface of earth by basically the radius of the earth. So, this is a fixed r, and at a fixed r, then the force will appear to be constant. But if we talk about large distance like interplanetary distance, then the gravitational force, we will see the variation of the force with the distance. So, the difference I want to point out is the following, that if I take this as an object and if I want to draw the force free body diagram, then we usually treat the earth and the interaction between the earth and this object. So, this object is our system, and then we can treat the gravitational attraction as an external force acting on this object. However, if we, so this is our force method. However, if we analyze the energy of the system, the gravitational energy, so for any potential energy, you need two bodies to define the potential energy. So, in this case, if you are talking about the potential energy, then you should include the earth in your definition of the system. So, for example, if you usually for a isolated, so if you consider the earth and this object as part of your system, so your object, let us call it a book, then that forms a closed or isolated system, and for which the total energy, the sum over kinetic energy plus potential energy will remain constant. So, but here you need to, the point is that you need to include the earth to define this kind of potential energy. So, these are certain conceptual points. Now, we are ready to apply what we have learned so far. So, we are going to now take some examples and some very important examples, and where we are going to apply everything that we are learned so far in the course. So, we are going to apply the Newton's laws, we are going to apply the momentum balance, we are going to apply the energy balance. So, the first example that I wish to discuss is the projectile motion. Now, my aim here is to take the projectile motion that is typically discussed in the textbook and critically review different aspects of that and compare what the projectile motion in real life versus what is described in textbook. So, the typical textbook projectile motion is throwing a ball in air, such as what I shown in this diagram. So, you start from some position which you call the origin, and then you take the horizontal direction as x axis and vertical direction as y axis, and this trajectory defines the position, and the blue arrow describes the instantaneous velocity of the ball at different points along the trajectory. because these positions and velocities are vectors, so we can resolve this motion into two independent components, one along x axis, one along y axis. And if you look at the x component, so imagine that the ball is creating some shadow on y axis and a shadow on x axis. So, as the ball is moving, the shadow on the x axis and y axis are also moving. Now, in typically you analyze this problem with in the presence of gravity. So, the gravity is acting in the along the y direction. So, that means in the x direction there is no force. Hence, if we apply Newton's law, we get that the acceleration along x direction is 0, and as a consequence the shadow on the x axis of the ball will move with a constant velocity, and hence if you plot the x coordinate of the ball as a function of time, you will get a straight line. Now, here one thing is important to again remind you that Newton's law is a initial value problem, which means if we want to measure the actual position and velocity at any instant for the ball, we have to mention the initial position and initial velocity of the ball. Without that, we cannot determine the subsequent position and velocity. So, this is about the horizontal motion, and in the vertical direction what we have is the gravity is acting downwards, and as we said that this is a constant force. So, you get a constant acceleration downwards, and if you solve it, you find that the y coordinate, the shadow of the ball along y axis as a function of time follows a parabola, and so as shown in this figure. So, then you can eliminate time from, so we have x as a function of time and y as a function of time, and then you can eliminate time from both these expressions, and finally you can get the trajectory y versus x. So, this is called the space evolution trajectory of the particle. So, this is called a time evolution trajectory, where you show the position as a function of time, and this is the space trajectory, the actual path that the ball is taking, and as you know that this path is also a parabola. So, I am not shown till the origin, so you can sort of extend the parabola. So, this is your famous parabolic path. Okay. So, let us now, so this is what I am sure that you have already learned in textbook. So, let us now critically review this projectile motion. So, what happens in real life? First thing is that there are certain, so this example is kind of idealistic, which means that there are certain assumptions made in analyzing this problem. And what are these assumptions? So, we are going to list one by one. So, the first assumption is that the acceleration due to gravity g is a constant. Now, as I mentioned that this g is, if you apply the Newton's laws of gravitation, then you get the expression for the acceleration due to gravity, and where this capital M is the mass of the earth and capital R represents the distance between the center of the earth and your object, and on the earth's surface R is basically constant and g is a universal constant of gravitation, hence this acceleration due to gravity is constant. However, when we talk about projectile, we should not restrict about motion only on the surface of earth. We should also be able to analyze satellite motion, for example, and if we want to include the satellite motion, then this condition is no longer true. In fact, this is easy to show that if you assume that g is not constant, but is given by this more accurate version of the gravitational force, then you can never get a parabolic trajectory. So, the trajectory that you get are two kinds of trajectories, one which is a closed trajectory such as the trajectory of earth around the sun, this is an ellipse. The other is a open trajectory which is not a closed circuit. So, these trajectories are either an ellipse or an open trajectory which is an hyperbola. So, this is called the Kepler problem of Kepler's two body problem, where two bodies which are interacting with each other via the Newton's law of gravitation. Then what is the space trajectory that they are following? So, this is a very standard problem in classical mechanics, in a more advanced course on mechanics, and the answer is that either you get a closed loop which is an ellipse, or you get an open loop, open path which is an hyperbola. Many comets follow this kind of trajectory, but you never get a parabola. So, parabola is really an approximation of a ellipse or an hyperbola. The second assumption, which is also very standard, is that usually we talk about when we throw the projectile, we stand on a horizontal ground, but this need not be true. For example, you can also stand on an inclined plane and throw the projectile, and in this case all your standard results about like what is the distance of throw, angle of throw, such that it will move the longest horizontal distance, the standard answer is 45 degree, that will no longer be valid if your ground itself is inclined. So, these things are you can you can sort of still include in your analysis. It is just makes your analysis little bit more complicated in terms of the mathematics. However, there is a very crucial point that makes this textbook example completely ideal and not very realistic, which is that we assume that gravity is the only force. Now, this is misleading and not fully correct. For example, we have already seen that in our real life we are immersed inside a fluid, that is the air around us, or it could be water if we are talking about projectile motion under the sea. In this case, the effect of the fluid you should never ignore. We have already seen in the context of when our discussion of drag force that this effect, this friction due to the fluid leads to the something called the terminal velocity, which is not present in our ideal example of projectile. So, now we are, when I talk about projectiles, we are no longer only thinking about a ball, but also something like a raindrop, which is also an example of projectile. I also want to mention, but this is beyond the scope of this course, is that sometimes the forces, the trajectories are random forces also play very important, and I am talking about the example of a coin toss. Coin toss is also an example of a projectile motion, but it is an unusual example in the sense that here we do not know what is going to be the actual trajectory, in the sense that we do not know whether we are going to get a head or tail as an outcome of a toss. So, in this case the random forces play an important role. So, what are the additional forces that are present in a real life projectile motion? So, one force, as I already mentioned, is the drag force. So, this is the friction between a solid and a fluid. Another force, there are two important forces that are also present for various kinds of projectile motion. For example, when one force we are going to talk about is the lift force. So, this is again an effect of the fluid through which the projectile is moving. So, and this is a force which is responsible such that for which, due to which the if you think about the bird that flies through air or a plane flies through air, so their motions, their flies are possible. So, here again I want to emphasize that projectile is not only about a ball. So, the bird flying through air is also an example of a projectile motion, and if you want to analyze understand those motions, then you also need to include the lift force. So, we are going to take an example of that perhaps in the next lecture. Another important force that we are going to talk about is a thrust. So, this force is essential for rocket motion to be possible. So, rocket is a projectile which can move through a deep space where no fluid such as atmosphere is present. In that case, there is no lift or no drag, but still we need some force to accelerate the rocket, and the origin of that force is the thrust. So, there are other, of course, there are various other additional forces that might be present. So, we mentioned these forces which are sort of very important for in real life, and we are going to understand their role through examples in the next lecture. Till then, see you. Thank you.